This video is brought to you by thepuzzler.com. Today is session number 4 of the Puzzler's AMC 10 course. We'll be looking at geometry on the AMC 10 test today. We'll look at topics ranging from power of a point to Pick's theorem in class today. Today's class is the final class of our AMC 10 course, and it will be more theory-oriented and less problems since there's just so much geometry content that we want to cover. Today's class will also cover pretty hard problems since it's the last class in this course, so there might be a lot of questions that you have, and feel free to ask those questions in either the comments or just rewatch the video as many times as you need until you understand the material. Let's get started. Our first topic for the day is triangles. Specifically, different ways to find the areas of triangles. Now, the most common way is base and height. If you have a triangle which has a base b and a height h, then the area of that triangle is just b times h divided by 2. You've probably seen this one. But let's look at some of the more or the less common ones that you can use to find the area of triangles. So you can also use trigonometry. The area of any triangle with sides A, B, C, opposite angles A, B, C, is A times B times sine of angle C divided by 2. Now we'll be going into more detail into this later on when we go into our trig section for today. But basically, if you have some, let's say, some triangle like this side equals A, this side equals B, this side equals C, then this angle would be C, this angle would be A, this angle would be B. So the angle is just opposite the side. And the area of this is just multiplying this side times this side, divide that by 2, and then multiply by the sine of this area, or this angle. The next one is also a pretty common one, Heron's formula. The area of any triangle with sides A, B, and C is the square root of s times s minus a times s minus b times s minus c, where s is a semiperimeter. And you have to remember that s is a semiperimeter, so the way that we find the semiperimeter is the sum of all three sides, and since it's a semiperimeter, you divide by 2. So s in this formula is equal to a plus b plus c over 2. So it can get a bit computational, but if you have all three sides and you can't use another method like base times height, you can always use Heron's formula. Okay, so the area of a circle with in radius r and semiperimeter s is r times s. So if you have a circle, if you have a triangle that looks something like this, and then you have a circle, so the incircle, right? That's a circle that's inscribed inside the triangle. The radius of this circle, right here, times the semiperimeter of the triangle, which is a plus b plus c divided by 2. That's s. That would give you the area of a, b, and c. That would give you the area of triangle a, b, c. You can also use the circumradius, which is the radius of the circle in which this triangle is inscribed. So if you have a triangle like this, the circumcircle would look something like this. So the circumradius would be wherever the midpoint is to one of the points. So a circle with circumradius r and side lengths a, b, c has area ABC divided by 4r. Okay, so this one's pretty cool. It's called the Pick's theorem. And the Pick's theorem expresses the area of a polygon, all of whose vertices are lattice points. So lattice points are points that are, let me write it here, that are integers. So no decimals, no fractions, only integers. They can be negative, but they need to be integers. So integers. Okay, so our lattice points in a coordinate plane in terms of the number of lattice points inside the polygon. So that's what you need to know, and the number of lattice points on the sides of the polygon. So the formula for that is, it's a bit complicated and we won't prove it today, but it's pretty cool. You can always look more into this if you're interested into the proof. The area is equal to I plus 1/2 times b minus 1, where I is the number of lattice points in the interior of the triangle, or any polygon. It doesn't even have to be a triangle. It can be any polygon. And b is the number of lattice points on the boundary. So let's look at an example. By the way, this theorem is pretty specific, and it won't always work when you're not given some sort of a diagram that you can make on a coordinate plane like this. But when it does work, it can really make your life much easier. So let's try to find the area of this polygon. So this polygon right here, there's two different ways we can find the area. First, we can try splitting it up into tiny different shapes that we do know how to find the area of, or we can use the theorem that we just learned. Let's try both ways. So our theorem, if we scroll back up, it says it's I plus 1/2 b minus 1. So I is the number of lattice points in the interior. Let's see. There's this point right here, this point, and this point. That gives us 3. Then the number of points that represent b is the number of points that are on the boundary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Just double checking my counting. Yep, 13. So 3 plus 13 divided by 2 minus 1. Because we have to multiply b by 1/2. This right here, this would give us 2 plus 13 over 2. 13 over 2 is 6.5, so this would give us 8.5. Right? Or you can write it as 17 over 2. Okay, let's double check our answer now. Let's go back here and split it into stuff that we do know how to find the area of. Let's erase all these dots. Okay, so first things first, I see the square right here. The square is a 2 by 2 square, so it has an area of 4. Then I have this small triangle right here with side lengths 1 and 2. So that would just be base times height divided by 2, so this has an area of 1. Okay, it's harder to find the area of this shape. But what I notice is that right here, 1 and over 2, and then 1 and over 2. So this point, and this point all fall on the same line. Which means that I can extend this line, and we have another triangle with base 2, and the height of this triangle is also 2. So 2 times 2 divided by 2, that gives us another area of 2. Now this has a base of 3 and a height of 1. 3 times 1 divided by 2 gives us 3 over 2. 4 plus 1 is 5. 5 plus 2 is 7. 7 plus 3 halves is going to give us 8.5 or 17 over 2. So that's just one way of showing that these two give us the same answer. Let's move on. A more general form of the Pig's theorem is the Shoelace theorem. Suppose the polygon P has vertices A1, B1, A2, B2, all the way to AN, BN, listed in clockwise order. Then the area A of P is equal to A equals 1/2 times the absolute value of these products, so A1, B2 plus A2, B3, all the way to AN times B1. So we eventually loop around, and don't worry if you don't see the connection here, I'll show that in a second. And then we subtract from that the products B1, A2, B2, A3, all the way to BN, A1. So we'll loop around again. And we can also do this in counterclockwise order, but you just need to use the absolute value of the answer so that if you get the negative version of the answer, it'll just become positive. And it gets its name because if you list the coordinates in a column like this, so that's what you want to do, list the coordinates in a column like this. And then you want to rewrite the first coordinate. You also want to rewrite that at the end. Then what this product is basically asking you to do is multiply A1 times B2, A2 times BN, AN, all the way to AN times B1. And then we're subtracting the products going the other way, which is B1 times A2, B2 times times A3, all the way to BN minus A1. Right? So that resulting image looks like laced up shoes, which is where this word comes from. And let's look at a quick example of this. We have 2019 AMC 10A. Two lines with slopes 1/2 and 2 intersect at 2, 2. What is the area of the triangle enclosed by these two lines and the line x plus y equals 10? Okay, so we have 3 lines. We have 3 lines, and we can find the equation of all 3 since we're given a slope and a point, which is point slope. We're also given another slope and a point, which is point slope, and then we're given the third equation. So we can find the intersection of all 3 of these, and that would be the easiest way to solve this problem. Let's take a look. So we have the first equation. It's going to be line with slope 1/2. So we have y equals 1/2 x. You can also use point slope, but generally point slope tends to just give you an equation. And if you're trying to solve for specific values, it can get more computational. So I'll just use slope intercept. So y equals 1/2 x, and 2 comma 2 needs to be a point. So if I plug in 2 for x, so if x equals 2, then what do we have? Then we have 1/2 times 2 gives us 1. So then you need to add another 1 to get the y coordinate to equal 2. And then the other equation is y equals 2x plus what? Or it could be also minus something. So 2 times, and then x equals 2. So 2 times 2 is 4. And just like I said, it is minus. So 4, you need to subtract 2 from it for y to equal 2. Make sure you see why this is true. Plug in 2 comma 2 into both of these equations, and they are valid points. Third equation is x plus y equals 10. I'm going to rewrite this in slope intercept form. Y equals negative x plus 10. So what are our 3 intersections now? So one of the intersections, the intersection of these two, is already given to us. That's going to be 2 comma 2. Now we just need to check the intersection of these 2 lines and these 2 lines. Let's tackle that one at a time. So we know that y is equal to negative x plus 10 from this third equation. And we also know that y equals 1/2 x plus 1 for the point that's on both of those lines. So y equals 1/2 x plus 1. And now we just have an equation in one variable, so we can solve this. Minus x, and then you want to subtract 1/2 x from both sides, so you get minus 3/2 x equals minus 9. So x is equal to minus 9 times 2 over 3, negative 2 over 3. So x is equal to negative 3 times negative 2, which gives us 6. So this point right here would be negative 6 plus 10. So that would be 6 comma 4. Right? If we plug in 6 right here, we're going to get 6 comma 4 as our answer for this one. Okay, let's look at the next example, which is 2x, next equation. So which is that 2x minus 2 is equal to negative x plus 10, or that 3x equals 12. So this means that x equals 4, and plugging in 4 here, we get negative 4 plus 10. That gives us 6 as our coordinate. So our coordinates are equal to, let's go here, they're equal to 2, 2, 6, 4, and 4, 6. So if I were to draw a rough sketch here, we'd see that 1, 2, 2, 2 would be here, 4 comma 6 would be somewhere here, and then 6 comma 4 would be right here. Right, so if you see with a triangle, it doesn't matter what order you put the 3 points in, since the 3 points are connected to each other. So let's just say it's this order right here. So we have 2 comma 2, 6 comma 4, 4 comma 6, and then for the shoelace theorem, you need to put the last point again, so that would be 2 comma 2. So now if you go back, we take the products from left to right, all the way to bottom, and then we subtract the products from right to left. Let's do that. Okay, so left to right, that's going to give us 2 times 4, which is 8. Then we add in 6 times 6, which is 36, plus 8. That's it. Now we subtract 2 times 6 right here, which is 12. Then subtract 16 and 12. So 16 and 12. So this gives us 8 plus 36 is 44, plus 8 is 52. Minus 12 minus 16 is minus 28, and then minus 12 gives us minus 40. So this gives us 12. So the absolute value of 12 is just 12. And now you have to remember one thing, and this is something that people tend to forget a lot, is there's this 1/2 right here. So now you need to do 12 times 1/2, which gives you an answer of 6. Let's move on. Let's now look at a couple of AMC 10 problems regarding triangles and their areas. So we won't be looking at any problems, or we won't always be looking at problems where there's directly a triangle given to us. For example, here we have to find the area of the shaded region, and I can't find any triangles in this diagram. But usually you can break apart the problem where you're asked to find the area of complex shapes. You can break it apart into triangles so that it's easier to find the area of that. And let's try that here. So it's very hard to find the area of the shaded region directly. But what we can do is, we're given a lot of side lengths, In fact, we know that this total side is 7 plus 1, or 8, and this total side length is 5. So the total is 40. We're given a lot of side lengths, right? We can do that and then subtract the white area, and we'll be left with the shaded area. And let's try that. So to find the area of the white material, we have some things that we can do. So first, let's put it like this. Okay, we have a rectangle right here. This rectangle, this rectangle, this triangle, this triangle, this triangle, and this triangle. And we know the side lengths of all those triangles. So by symmetry, we know that this right here is the midpoint. This is the midpoint of the rectangle. So this total thing is 8, right? So this side right here is 4. This total thing is 5. So this side is 5 over 2. By that, I mean just the half, right? So this over here is 5 over 2. So then this is 1. So then this needs to be 3 over 2. Similarly, this needs to be 3. Okay. So it's enough to find the area of this region right here and just double that. We can find the area of this half rectangle and just double that to find the area of the other shaded region, right? So finding the area of this shaded region and then doubling that to find the area of the other shaded region. So the area of the top rectangle, the full area, is 8 times 5 over 2, which is 20. Now we need to subtract from it this rectangle right here, which is 4 times 5 over 2, which is 10. So 20 minus 10 gives us 10. Now we need to subtract from it this triangle right here, this triangle right here. And this has side lengths 3. So this has a base of 3 and a height of 5 over 2. And then you also need to multiply by 1/2 since it's a triangle. And that gives us 15 over 4. So that's 15 over 4. This right here, this is going to be, so this total thing is 5 over 2. So this is 3 over 2. And this right here is equal to 4. 3 over 2 times 4. That gives us, let's write it out, 3 over 2 times 4. And then we multiply by another 1/2. That gives us 3. So we have 10 minus 3, which gives us 7. And then we need to subtract the 15 over 4. 7 minus 15 over 4. Now that's the area of one of the shaded regions. We need to double that. So we get 14 minus 15 over 2. 14 minus 15 over 2. Well, 14 is equal to 28. So over 2 minus 15 over 2. That's equal to 13 over 2. So scrolling a bit down to look at the choices, our final answer is 6 1/2. So let's move on to the next problem. Okay, we're given triangle ABC. AB equals 6, AC equals 8, BC equals 10. And right away, I noticed something. 6, 8, 10, that's a right triangle. So let me draw my diagram. They didn't tell us it's a right triangle, but by the Pythagorean theorem, we know that it has to be a right triangle. So we have that AB equals 6. So I'll make this point right here. Okay, so A is this point right here because A, B, and AC are the legs. And then AC is a longer leg, so let's make this point C and this point B. 6, 8, 10. And D is the midpoint of BC. So D is the midpoint of BC. What is the sum of the radii of the circles inscribed in ADB? Okay, so let's put D and let's draw in AD since AD is the side length of ADB. And ADC. Okay, so we have a circle like this. And we have a circle like this. And we're asked to find the sum of the inradiuses, right? Well, what do we know here? For a right triangle, whenever you do this, whenever you draw a median, first you're splitting this hypotenuse into 2 because that's the definition of a median. But this side length right here is also equal to 5. That's also equal to the half point. Further, this point right here, if you're finding the median to the hypotenuse of a right triangle, that's actually the circumcenter of the circle, right? If you were to draw a circle around the triangle, that would be the circumcenter, which proves why this is 5, right? It's the radius is 5. So we have 5, 5, and 5. Okay, what do we do now? Well, is there any connection between the inradius and the information that we do have? Let me just write out the side lengths here. 8, 5. Well, we did, not 5, 6. 8 and 6. Well, we did learn about how to find the area of a triangle using the in radius. Let's scroll back up to take a look at that. So we said that to find the area of a circle, granted that you know the in radius, it's just r times s, where s is the semi-perimeter, right? So maybe we could use that. Let's see how we would use that. So scrolling back down. Okay. Do we know the area of this triangle? This triangle right here, ADC. And do we know the area of triangle ADB? If we know the area, we already have all three side lengths. So we can divide by the side lengths to get the... We can divide by the semi-perimeter using those side lengths to get the radius, and then we can add up those radiuses. And actually, let me pull out AC and D. ACD. ACD is a 5, 5, 8 triangle. Now the cool thing about isosceles triangles is you can put a line in between, and this bisector right here, this median, it also creates right angles. So this right here is 4, and then by Pythagorean theorem, this is 3. We know that the area of this triangle is 8 times 3 divided by 2, or 12. Right? So we're given that 8 times 3 divided by 2, that gives us 12. And we're given that this is equal to S times R using our formula. So 12 is equal to S. What is S? S is 5 plus 5 plus 8 divided by 2 times R. That's 12 equals 5 plus 5 is 10. 10 plus 8 is 18. 18 divided by 2 is 9. 18 divided by 2 is 9. So this equals 9R. So then R is equal to 4 over 3. Okay, we found one of the radiuses. Let's see if we can find the other one. Let's draw in that triangle. We have, once again, 5, 5. And we have 6 again here instead of 8. So we can do the same thing. Let's divide it in 2. Right angles again. This is 3. By Pythagorean theorem, this is 4. So we have 6 times 4 divided by 2, which gives us 12. So 12 is equal to 5 plus 6 divided by 2 times R. Okay. Almost done. So 12 is equal to... By the way, if you want to be a bit more specific about the notation, you can use R2 instead of using R, since it's a different radius than this one right here. So 12 is equal to 10 plus 6 is 16 divided by 2 is 8. So 8 R2. So R2 is equal to 3 over 2, since 12 over 8 equals 3 over 2. So radiuses are 3 over 2 and 4 over 3. And we're asked to find the sum of them. 3 over 2 and 4 over 3. Well, the sum of these, just find the common denominator. That's 8 over 6 plus times 3, so 9 over 6, which gives us 17 over 6. And sure enough, that's a choice. Let's move on to the next problem. 2018 AMC 10A. Farmer Pythagoras has a field in the shape of a right triangle. The right triangle's legs have lengths 3 and 4 units. In the corner where those sides meet at a right angle, he leaves a small unplanted square S so that from the air it looks like the right angle symbol. The rest of the field is planted. The shortest distance from S to the hypotenuse is 2 units. What fraction of the field is planted? Okay, so for this problem, we're basically asked to find the area of the white area over the total triangle. Okay, so we know the area of the total triangle. That's given to us 3 and 4, right? 3 and 4, you multiply them, divide by 2, you get an area of 6. But we don't really know how to find the area of the white regions. Luckily, we can draw in some lines and split it into easier triangles to make the problem easy for us. Now, I went ahead of time and I drew in a diagram. And here we can see how to solve this problem. Let's say the square has a side length of x. Then we can find the area of all the triangles and then use that to find the value of the triangle, because the red triangle plus the yellow triangle plus the green triangle must equal the area of the total triangle, which we know is 6. So let's do that. So the area of the red triangle is 3 as a base times the height of x divided by 2 plus The area of the yellow triangle is 4 times x divided by 2. And then the area of the green triangle, well, it has a height of 2 with base 5. So that's 5 times 2 divided by 2, which is 5. And this is equal to 3 times 4 divided by 2, which is 6. So 7x over 2 equals 1, or x equals 2/7. If x equals 2/7, then the area of this square right here, that's equal to x squared, which is 4 over 49. So the total area that is planted of this field, that is not planted of this field, is the area of that square over the total field. So that is 4 over 49 over 6, which is 4 over 49 times 6. We can cancel out one of the 2 to give us 2 and 3 here, which is 2 over 147. Okay, so that is the area of the field that is not planted. The problem is asking us for the area of the field that is planted. So we would subtract that from 1. 1 minus 2 over 147 gives us 145 over 147. And just like that, we just solved the final 5 AMC 10 problem. Let's move on. In the next part of our class, we're going to be looking at special right triangles, which are definitely one of the more important parts of the AMC 10 test, right? Especially on the later end, you really need to know your 30, 60, 90 and 45, 45, 90 triangles. So whenever you have a 30, 60, 90 degree triangle, and if you call the hypotenuse h, then the side opposite the 30 degree angle is equal to 1/2 h, and the side opposite the 60 degree angle is equal to square root of 3 over 2 times h, right? So h could be any number. For example, if h is 1, then this side would be 1/2, and this side would be root 3 over 2. So these numbers, you should just memorize them. That's the best way to do it. And you can actually prove that this does work using the Pythagorean theorem. Although why these exact numbers, you do need to know a bit of trick for that. Okay, the next type of triangle is a bit simpler. 45 degree, 45 degree, 90 degree triangle. Here, you can say that these two sides are k. Since it's an isosceles triangle, right? Two angles are the same. The two sides have to be the same. And then using the Pythagorean theorem, you know that the third side is root 2 over k. So that is something that we can prove. Okay, we won't look at too many problems since these just show up so much that they'll eventually and inevitably just show up in other problems that we do. But let's look at one problem. The 2000 AMC 10. In rectangle ABCD, AD equals 1, P is on AB, and DB and DP trisect ADC. So where's DB? DB is right here, and DP is right here, and they trisect ADC. Well, I know it's a rectangle, so ADC is 90 degrees. So if we trisect it, each of these angles is 30 degrees. And actually, I can even go further to notice that this is a right triangle, so this has to be 60 degrees. That's it for now. Now it's asking, what is the perimeter of triangle BDP? We're asked to find the perimeter of triangle BDP. Now we know that this right here is also a right angle, so this is 60 degrees. And since angle B is a right angle, this is 30 degrees. And then since the total measure of a triangle is 180 degrees, and we have two 30-degree angles, this is 120 degrees. Okay, so we're given that this right here is equal to 1, and that's the only side length that we have to work onwards. And we need to find PD plus PD plus DB plus PD plus PB, right? And you can notice that since it's an isosceles triangle, we have that PD equals PB. Okay, so if this right here is equal to 1, then this right here, well, we said that, if we scroll up, we said that the side opposite the 60-degree angle, that's equal to root 3 over h, root 3 times h over 2. And then this right here is equal to 1/2 h. So root 3 h over 2 is equal to 1. So what is h equal to? H is equal to 2 divided by root 3, or 2 root 3 over 3. Okay, so if we plug in h right here, we get that 1/2 times h, 1/2 times h That gives us root 3 over 3. And then this is just h. So this is 2 root 3 over 3. We also know that this is 2 root 3 over 3. And now we know the total value of side AB. Side AB is equal to 2 root 3 over 3 plus root 3 over 3, which is 3 root 3 over 3, which is root 3. So AB equals root 3. Now AD equals 1. And since DB is just the hypotenuse of triangle ADB, we can use the Pythagorean theorem here. Root 3 squared plus 1 squared gives us 3 plus 1, right? 3 plus 1, that gives us 4, and the square root of that is 2 squared. So this third side right here, this right here is equal to 2. Just double checking that. 3 plus 1, that gives us 4. Yep. So this side is equal to 2. And actually, this is also a 30, 60, 90 degree triangle, but you can just use the Pythagorean theorem. You don't need to overcomplicate stuff for yourself. Okay, so we know that DB equals 2. DP equals 2 root 3 over 3. And since PB and PD are equal, we have BP equals 2 root 3 over 3. So this total perimeter of triangle BDP is equal to 2 plus 2 times 2 root 3 over 3, which is 4 root 3 over 3. Let's see if that's a choice. And sure enough, I see that that is equal to choice B. So this problem wasn't too hard, but the key thing is that you need that 30, 60, 90 degree triangle to start off and find the length of this triangle right here. I mean, this side length right there and this side length right there. So that's basically what we build off of. And that's usually how you're going to be incorporating 30, 60, 90 degree triangles into the solution for the AMC 10 problems. Let's move on. It's giveaway time. We'll be raffling away 2 Wolfram-Alpha Notebook Editions valued at $50 each. And you can enter this giveaway by going to thepuzzler.com/amc-10-course-giveaway. So the winners of the last giveaway, which was an Amazon gift card, a $15 Amazon gift card each, were Akash Pratap and Alina Zeng. You can email us to claim your prize. Don't forget to subscribe and like this video if you haven't already. It really gives us that boost in the YouTube algorithm. Okay, so the next topic is angles and polygons. So the sum of the interior angles of any n-sided polygon is 180 times n minus 2, where n is just the number of sides that the polygon has. It follows that the angle measure of any polygon, of any angle of a regular n-sided polygon, is the total degrees, which is 180 times n minus 2, divided by the number of angles there are, which is n. So that's where we get that formula for. So how many degrees are in an octagon? So an octagon has 8 sides, so our formula would become 180 times 8 minus 2, which is 180 times 6, which is 360 times 3, or 720 plus 360, which is 1080 degrees. What is the measure of an angle of a regular octagon? So we just divide this 1080 degrees by 8, and that would give us 1. And we have 28, so that would give us 340, which would give us 5. So 135 degrees is the average angle, or is the angle of a regular octagon. Okay, so those formulas were pretty basic, but let's move to the next topic, which is cyclic quads. A cyclic quad is a quad that can be inscribed in a circle. They have a number of interesting properties. Opposite angles of a cyclic quad always sum to 180 degrees. So one important formula that we have with cyclic quads is the Ptolemy's theorem. So given a cyclic quad ABCD with side lengths A, B, C, D, and diagonals E and F, so side length A corresponds to the side opposite point A, we have that AC plus BD is equal to E times F. Let's see what that means in a specific problem. In triangle ABC, we have that AB equals 7, AC, so let's label that AB equals 7, AC equals 8, BC equals 9. So this thing equals 9. I won't label that, I'll just say BC equals 9. Point D is on the circumscribed circle, so I already drew in the circumscribed circle of the triangle so that AD bisects angle BAC. Okay, one thing you need to know about cyclic quads is that if two angles subtend the same arc, or arcs of equal length, then the angles are equal. So here we know that DAD bisects angle BAC. So these two angles are equal. And thus, that means that the angles they're subtending are also equal. So BD is equal to DC. Now CBD also intersects or subtends the arc DC. So thus, it's also equal to the angle BAD. And similarly, this angle right here is also equal. So angle ECD is also equal to the other three angles. Okay, so it's asking for the value of AD over CD. Now, AD is just the total length. Let's just say AD. Okay, AD, we don't know what to do about that. And then CD. So CD, let's give it some variable. Let's call it Y. CD is equal to Y. Do we know what else equals Y? Well, sure we do. We know that BAD and DAC are equal. So the arcs that they're subtending are also equal, BD and DC. So then those chords are equal. So this is equal to Y. And now, I don't even need to go further because I see the application of Ptolemy's theorem right here. Opposite angles, we have all the sides, and then we have one of the diagonals, and we need to find the other diagonal, right? This diagonal is 9. And the quad that we have is ABCD, right? So it's ABDC. ABDC. So the opposite sides are 7y, and the product of the other two opposite sides is 8y. And this is equal to AD. So AD times BC. Now we know that BC is equal to 9 and AD is equal to, well, we don't know what that is. It's AD. So 15y equals 9 times AD. And what are we trying to find? Well, we're trying to find AD over CD. Well, CD is just y. So we're trying to find this ratio, and we have this equation. So that's possible. We can divide both sides by 9y. So on the right-hand side, on the left-hand side, we'd have 15 over 9 equals AD over y. So 15 over 9, that's just equal to 5 over 3. So our answer is B, and we can move on. So a formula that's basically Heron's formula, but for quads. Given a cyclic quad with sides A, B, C, D, the area K can be found as the square root of S minus A times S minus B times S minus C times S minus D, where S is equal to A plus B plus C plus D divided by 2, or just a semi-perimeter of the quad. So this is quite an important theorem, and you can probably see the resemblance that it has with Ptolemy's theorem. I mean, with Heron's theorem for triangles. Okay, power of a point theorems. So there's just basically three possibilities when you have power of point theorems. The first possibility is that the two lines are chords of the circle and they intersect out inside the circle. So for example, like this right here. In this case, we have that AE times CE is equal to BE times DE. You could also have something like this, where you have two lines, and one of the lines is tangent to the circle, and the other one is a secant of the circle. Here you have AB squared, so AB squared is equal to BC times the whole secant, which is BD. Finally, if both lines are secants and they come from the same point, then we have CB times the whole thing, CA, is equal to CD times the whole thing, CE. So these can be really helpful, and let's see why. So in angle ABC, AB is equal to 86, AC equals 97. A circle with center A and radius AB intersects BC at points B and X. Moreover, BX and CX have integer lengths. What is BC? Let's take a look at how to solve this problem. Okay, so the first step to solve this problem would probably be to draw a diagram. So let's do that. It's a good idea to start with a circle. You want to start with a circle because by doing that, it's easier to draw the triangle that'll go inside. Let's just try to make the circle a bit better. Okay. And then we have that ABC inside of here. We have that AB is the center. Then we have the radius, which is B. So radius is AB, so I can say this point is B. And then I have the third side, which is AC. And since AC is longer than AB, this is going to go a bit out like this. Let's draw in our triangle. And this will look something like this. So let's make it a bit more obvious what we have here. Let's draw it here. And then like this. Okay. So then AB right here, AB is equal to 86. So let's put that in really quickly. And then we're given that AC is equal to 97. So we can put AC right here. AC is equal to, so this should be 86, and then AC equals 97. So this is also 86, and this is 11. And we're asked, what is BC? Now, one thing that they do tell us is that BX and CX have integer lengths. That's quite important to know. But we can now try solving this problem using power of point. The power of point C, I'll just call that P of C for short, is equal to 11 times the secant, right? 11 times the full secant. And we can extend this so that it's a secant. And this is also 86 since it's just a diameter. And this is 11 plus 86 plus 86. That gives us 11 times 86 plus 86, that's 160, that's 172. 172 plus 11, that's 183. Now, if we call this point X, then we have that right here, we have, this is also equal to X times BC. So we have two variables, so this makes it pretty hard. But we're given that it has integer lengths, so maybe that'll help. What's the prime factorization of 11 times 183? Well, let's look at 11. Let's look at 183. 183, if you divide it by 3, it's actually divisible. So we can do 11 times 3. That's going to give us 61. And now I know that 61 is a prime number. Now, one thing that logically follows is that this right here, this is a straight line to the circle. This is the shortest distance to the circle that we can possibly have. And since it's the shortest distance, X is greater than 11. So if we write the factors of this number right here, we'll start out with 1, 3, 11. Next one would be 33, 61, and so on. We know that 1, 3, and 11 cannot work. So the minimum value for X is 33. So if X is equal to 33, then the whole thing, BC, is equal to 28, right? BC is equal to 28 because it has to equal 33 times 61 to equal this number. And BC is equal to 61, and this part right here is going to equal 61 minus 33, which is 28. So now what is BC? To find the measure of BC, just add up 28 plus 33. 28 plus 33, that gives us an answer of 61. So this problem is pretty hard, but if you realize that it's solvable using the techniques that we learn and that we're going to be learning in class today, you can draw a diagram and you'll eventually work your way around the problem, and you'll see that it's something that we can convert it to a simple power of a point problem and use a bit of number theory to solve the problem. Let's move on to the next problem. Next up, we have the two-tangent theorem. If two tangents intersect at one point, then both of the tangents are congruent. The diagram below shows us that AB and AC are two tangents that intersect at one point, right here, A. This means that AB and AC are congruent. Keep in mind that the congruent segments come from the intersection of the two tangents to the tangent point. So AB and AC, not C and something else and B and something else. It's AB and AC. So this is going to show us more power when we look at it in the context of an AMC problem. So here's a pretty hard problem from the AMC 12A. Square ABCD has side lengths 2, a semicircle with diameter AB is constructed inside the square, and the tangent to the semicircle from C intersects side AD at point E right here. What is the length of CE? Okay, so first thing I see is that EA is actually tangent to the circle, right? It just doesn't seem that way because it stops at the tangency point. So I can draw in another tangent right here, because EC is tangent to circle AB, because it tells us that the tangent to the semicircle from C intersects side AD at E. And now you probably see how I can apply the two tangent theorem. If I let this side be x and this side be x, I'm going to have tons of equations. So let's say this is the center of the circle. What do we have next? We have that square ABCD has side lengths 2. So this is 2. This is 2 minus x. Let's just make that better. Because the whole side is x, so then this is 2 minus x. CB equals 2. And we're asked for the length of CE. Okay, so how would we go about finding the length of CE? Well, let's draw in this radius right here too. And we know that this AB is equal to 2, so then this radius right here is going to be equal to 1. Okay. Does that help us in any way? Let's take a look. So we have this angle right here. Let's call this point some point G. We have that CB equals 2, GB equals 1. Well, using the Pythagorean theorem, we know that GC is equal to 4 plus 1, and then take the square root of that, which is square root 5. So GC equals square root of 5. And I'll just make it, I'll erase that curly line. So GC equals square root of 5. Now, whenever a radius intersects or touches a tangent, it makes right angles, right? We get a lot of right angles. And actually, there's a better diagram here. So tangents, they make right angles. Very important to know that whenever they intersect a radius or whenever they touch the radius, a right angle is made. So going back here, we see that this is a right angle, which gives us another Pythagorean theorem. This length right here, that's equal to, let's call it y. So y squared plus 1 squared is just 1. And then plus square root of 5 squared, which is 5. So y is equal to 2. So this is equal to 2. And now we can apply Pythagorean theorem on triangle DEC. 2 minus x squared plus 2 squared, which is 4, equals 2 plus x squared. Thankfully for us, the x squared terms will cancel out when we multiply this, so we know that this will give us one quick solution. Let's do it. X squared minus 4x, and then finally plus 4, and then the plus 4 that we already have, is equal to x squared plus 4x plus 4. So the x squareds and the plus 4, one of them cancels out, so we have minus 4x is equal to, or minus 4x plus 4 equals 4x, or minus x plus 1 equals x. Adding x to both sides, we get 1 equals 2x, or that x equals 1/2. Okay, well, x is this side length right here, so this is 1/2. So the total length of EC is 1/2 plus 2, which is 4 over 2, which gives us 5 over 2. So our final answer is D. And we solved that hard problem just by applying all the theorems that we know, including Pythagorean theorem, two-tangent theorem, and other ideas that we know. Okay, one very important topic and something that most AMC 10 students have familiarity with already is similar triangles. So just to review, there's 3 different types of ways to know if two triangles are similar. There's double angle similarity. If two angles are in two triangles are similar, then the third angle is also congruent, which makes the two triangles similar. Then there's SAS similarity. If two triangles have two similar sides, which means that their corresponding ratios are equal, and the included angle between those two sides is congruent, then the two triangles are similar. And finally, we already used this, but the Pythagorean theorem, a squared plus b squared equals c squared. It works for any right triangles. A theorem that sometimes is quite useful in problems, and problems that use the angle bisector theorem can usually only be solved by the angle bisector theorem, is that if you have some line that bisects an angle, so this line right here, then the ratio A to B is equal to the ratio C to D. There's actually other forms of this that you'll sometimes see, which is that if you were to multiply both sides by b and divide by c, you'd get that a over c is equal to b over d. So this is quite helpful because there's some ratios that you can use when you have an angle bisector. Okay, let's look at something related to 3D shapes. Let's move on to the next part of our class and look at 3D shapes. So right here, I have a chart. And if you have a rectangular prism, let's just quickly review all the formulas that we know. A lot of these can be derived on the spot, but some of them, it's just very hard to come up with. There's no way to really know the surface area of a sphere without actually knowing the formula already. So let's scroll here. Okay, so we have that a cuboid, which is a rectangular prism, it has a surface area of 2h times L plus B. It has a total surface area of 2, so you don't need to worry about this column, doesn't really show up. Total surface, you don't need to worry about this column for this specific shape. The total surface area of a cuboid or a rectangular prism is just 2 times LB plus BH plus LH, and the volume is L times B times H. Now, a cube has all side lengths equal to A. So the curved surface area is 4A squared. So when they say curved, they're just not talking about the bases. That's usually what it means. So for like a cylinder, you would just not count the top and the bottom bases, which is why they have it for a cube, even though you might be wondering about the fact that they don't actually, there's no curved surfaces on a cube, but that's what they got that number from, or we got that number from. And then the total surface area, which you'll usually see, is A squared, which is the side length of one face, and then there's 6 of those faces, so 6A squared. The volume, well, it's just a cuboid, but each side is equal to A, so it would be A cubed. When you have a right circular cylinder, like the one shown here, the curved surface area is 2 pi r times h. The total surface area is 2 pi r times r plus h. And the volume is pi r squared times h. For a right circular cone, and you'll see some of these problems a lot on the AMC 10 because they like testing you on whether you know this, the curved surface area is equal to pi r L. L is equal to the slant height of a cone. And to find the slant height, if they don't give it to you, the way to find the slant height is, you can probably see it in this diagram, drawing a right triangle. So drawing a right triangle where height is h and the base is r, and then the hypotenuse is L, and you can use the Pythagorean theorem there to find the value of L given that you have h and r. The total surface area is pi times r times L plus r. And the volume is 1/3 times pi r squared times h. So 1/3, basically, it means that there's 3 cones that can fit in the appropriate cylinder. Okay, if you have a sphere, there's no curved surface area because all of the areas are curved. So it's just the total surface area, which is 4 pi r squared. The volume is 4/3 pi r cubed. Now, this is something that you can derive on the spot, but it's still good to know it if you want to. A hemisphere has a curved surface area of 2 pi r squared because it's just half of the normal sphere. But the total surface area is 2 pi r squared plus the bottom face, so that would make it 3 pi r squared. And the volume is just the volume of a sphere divided by 2, so 2/3 times pi r cubed. Let's look at a 3D problem. Okay, before I start this problem, whenever you see 3D problems on the AMC 10 or the AMC 12, and especially when they appear later on, you don't really need to know too many formulas, like basically the simple formulas that we went over. After that, you can actually convert the problem into some sort of a 2D problem and then use the techniques that we've learned so far to solve that. Let's see what I'm talking about. So this is from the 2004 AMC 12A. A pyramid has a square base with sides of length 1 and has lateral faces that are equilateral triangles. A cube is placed within the pyramid so that one face is on the base of the pyramid and its opposite face has all its edges on the lateral faces of the pyramid. What is the volume of this cube? So I drew in this diagram, but it's not too hard to draw, right? And that's usually the first thing that you want to do when you see a 3D problem. Try to imagine what it would look like so you can see how to actually go about solving the problem. So for these problems, it's just important to determine what the cross section is. And that's something that comes with practice, right? You want to convert this 3D problem into a 2D problem. And you can do that by taking the appropriate cross section of this. Now, let's plug in some of the sides that we know. We know that this is 1, because it's all equilateral. It says equilateral triangles right here. Now, one possible cross section I might take is this and this. So I'm chopping it in half. But that seems a bit complicated, right? We don't know the length of this side. We could probably find it, but we don't yet. And we don't know the side lengths we don't know the height and stuff like that. We can probably figure it out, but I see an easier way to do the problem. What if we take a cross section across this line right here? So our triangle cross section looks something like this. Then we have a triangle with a rectangle inscribed in it. And this rectangle, let's say it has a height x, right? And x corresponds to the height of the cube. So I'll just label that there. Then this right here, this is a diagonal. This is a diagonal of the cube. So it's equal to x root 2. Now, what else do I know? Well, for this triangle, both these sides are equal to 1 and 1. And this diagonal right here, that's equal to a 1, 1, root 2, right? That's a 45, 45, 90 triangle. So this equals root 2. That tells us that this right here, this is the 1, 1, root 2 triangle. So that tells us that this is 45 degrees, 45 degrees, and a right angle. But wait a second. We also know a lot of other stuff. This, since it's a rectangle, is a right angle. And thus, this is also a 45 degree angle. And I can label this as x since it's 45, 45, 90 triangle. Now this, since it's a rectangle, is x root 2. And similarly, this is 45 degrees. And since this is x, this is also x. So we have that 2x plus x root 2. This total side length is equal to root 2. Okay, that makes the problem into one variable linear equation, one variable equation that we can solve. We have that x is equal to 2 plus root 2. X times 2 plus root 2 equals root 2. Or x equals root 2 over 2 plus root 2, which is equal to 1 over 2 plus root 2. That means that right here we have, 1 plus root 2. Actually, we can't really do that. So, yeah, it would be, we need to divide 2 by root 2 and root 2 by 1. So that would be 1 plus root 2. Now we can multiply both sides by the conjugate to make it into a rational fraction. 1 plus root 2 and 1 minus root 2. So now this gives us 1 minus root 2 and then 1 minus root 2. And this gives us 1 minus root 2 over 1 plus root 2 times 1 minus root 2. That's 1 minus 2. So here I just use that a plus b times a minus b equals a squared minus b squared. And you can do that when you have when you have square roots or imaginary numbers in the denominator of a fraction to clear that out. So the bottom would become 1 minus 2, which is negative 1, or root 2 minus 1. Okay. So root 2 minus 1, when we cube that, since that's the side length of the cube, what do we get? Well, root 2 minus 1, that's equal to root 2 minus 1 squared, which is 2 minus 2 root 2 plus 1, or 3 minus 2 root 2. So 3 minus 2 root 2 times root 2 minus 1. That gives us, for the first term, we'll have 3 root 2. What else do we have? Then we have 3 root 2 minus 3. Then we have minus 2 root 2 times root 2, which is minus 2 times 2, so minus 4. And then finally we have minus 2 root 2 times minus 1, which is plus 2 root 2. This gives us 5 root 2 minus 7. Is that an answer choice? Sure enough, it is. So that means that the answer to this problem is 5 root 2 minus 7. So for this problem, it was pretty hard. And if you don't see one of the cross sections, maybe you tried some other cross section, but if you don't see a correct cross section, you sort of don't have anything to do. And for these problems, you just need to practice a lot of 3D problems until you get good at noticing what type of cross section can you take to best solve the problem. let's move on to the next topic. Okay, now as we're running out of time, let's take a look at some of the more theorems, some of the theorems that can appear on the AMC 10. Not as much, but you should still know them. The first theorem we're going to look at is a Stewart's theorem, and it allows you to calculate the length of a cVN. So cVN is just a line from a point of a triangle to the opposite side. So it's a line segment that extends from a vertex of a polygon to its opposite side. So medians and altitudes are all cVNs in a triangle, and they're just special cVNs. And the formula to calculate a cVN is this right here. M times n plus a times d squared. So m times n times a plus a times d squared. So a is the total length times d squared is equal to m times b squared. So this times b squared plus n times c squared. So n is right here, and then c is right here. So this is a pretty long formula, but it can be really helpful in problems that require its use. One way that I've used in the past to memorize it, and a lot of people have found this really helpful, is a man plus a dad put a bomb in the sink, right? Because you can rearrange the letters of this. You get man plus, if you were to distribute out the D, or like actually expand the D, you would get DAD equals BMB and then CNC. So a man and a dad put a bomb in a sink. So you can use that example or that device to help you memorize it. Next, even though we've hit some trig, just a formal review of trig. So a sine function, just the sine function of an angle that's in a right triangle, and it tells you the measure of that is the opposite side over the hypotenuse. So that you can use SO katoa to memorize all of these. SO just stands for sine opposite over hypotenuse. Then cosine is going to be adjacent side over hypotenuse in a right triangle, and you can use ka for that. And then for tangents, opposite over adjacent. So toa for that. So if you just remember SO katoa, that's a helpful device to help you memorize all three of these. But as you delve into trig further, what you'll see is that they're not just confined to right triangles. You can actually find the sine or cosine of any angle. Same thing with tangent. So we actually have a special law called the law of cosines. And it tells us that a squared, so the side a squared, is equal to b squared plus c squared minus 2 times bc, so b times c, times cosine of angle A, which is this angle. So the angle opposite the side that we're trying to find. So if you have side B and C and side A, you have this right here. One thing to notice is that if you have a right triangle and you're trying to find the hypotenuse, then cosine of A is just 90 degrees. So cosine of 90 is 0. So this just cancels out. And we sort of have the Pythagorean theorem here. A squared equals B squared plus C squared. So you can say that the law of cosines is just a more general form of the Pythagorean theorem. Or more specifically, the Pythagorean theorem is a specific form of the law of cosines. But that's not it. We also have the law of sines. This isn't as helpful on the AMC 10, but it doesn't hurt to know it. So side A over the sine of the angle A is equal to B over sine of angle B, and that's equal to C divided by the sine of angle C. And it's actually the same. You can reverse all the fractions if you need to. And here's the extended law of sines. So the extended law of sines, it's still the same thing, but it tells that it's equal to 2 times r. So 2 times r. R is just a circumradius, right? So if we were to put this in a circle right here, imagine that's a circle, then this right here is r. And you might be wondering, how do I know it's the circumradius and not the inradius? It's capitalized. When you use r as a capital, you're usually referring to the circumradius, while if it's lowercase, that's usually the inradius. So that's the extended law of sines. Okay, so we have a problem here. If the sides of a triangle have lengths 2, 3, and 4, what is the radius of the circle circumscribing the triangle? Okay, if you remember from all the way in the beginning of the class, we have a formula for getting the area of a triangle using the circumradius. Let's see what it is. So the formula is equal to A times B times C over 4R, where R is a circumradius. We also are given the three sides, so we can find the area using Heron's formula, since that's when it's the most useful. Heron's formula, well, the semi-perimeter is 2 plus 3 plus 4 divided by 2, which is 9 divided by 2, which is 4.5. Right? 9 over 2 equals 4.5. So the area of this triangle is 4.5. Let's just write it as a fraction. 9 over 2 times 9 over 2 minus 2, which is 5 over 2, times 9 over 2 minus 3, which is 3 over 2, and then times 9 over 2 minus 4, which is 1 over 2. This gives us 45 times 3, or 135 over 16. And we're taking the square root of this. Okay, so the top is equal to the 15 times 9, and then over 16. And the square root of this is just 3 root 15 over 4. Okay, so the area of the triangle is equal to 3 root 15 over 4. Now we already know the values of A, B, and C. They're given to us. So A, B, and C, that's going to be equal to what? That's 2, 3, and 4. Their product is equal to 24. So 24 over 4R is equal to 3 root 15 over 4. The 4's cancel out, and we can multiply both sides by R to get 24 equals 3 root 15 R, or 8 equals root 15 R. Divide both sides by root 15 to get 8 over root 15 equals R. And fortunately for us, that's an answer choice. Okay, so that just shows you the power of the circumradius and how you can use that. Imagine if you were given the circumradius here. You'd still be able to find the area of that triangle, so these formulas can be pretty useful. Let's take a look at one last problem before we wrap up for the day. Okay, so for the last problem for today's session, we'll be doing a problem from the 1983 AMC test. This problem isn't a problem number 1, 2, or even a problem number 3. It's actually a problem number 14 from the test. So yeah, it's supposed to be a hard problem. But using what we learned in today's class, let's try to solve it. So in the adjoining figure, two circles with radii 8 and 6 are drawn with their centers 12 units apart. At P, one of the points of intersection, a line is drawn in such a way that the chords QP and PR have equal length. Find the square of the length of QP. Whenever you see circles like this, let's zoom in onto the diagram. We have that whenever you see circles like this, what you want to do is connect or create the radiuses. So this right here is a radius, this is a radius, this is a radius, and this is a radius. And we know the side lengths, these are 8 and these are 6. So one important theorem that we have is whenever you draw a radius, and we don't even need to know any theorem for this, we just need to know that QP, and let's call these points A and B, and these points S and T. So whenever you have an isosceles triangle, here we have QPA, since QA is equal to PA, you can draw in the altitude, and that's also equal to the median. So this means that these two are equal, right? In an isosceles triangle, the altitude from to the base, the altitude to the base, is the same as the median, and it's the same as the angle bisector. Okay, so we have this right here. We're asked to find the length of QP squared. We know that this is x, and thus, since these two triangles are equal, QSA and PSA, this is also x, since we're dividing QP into 2. Now we know that PR equals QP, so these two are also x's. Okay. Well, looking at this problem, we've basically labeled in all the sides we know. So now we have to think about how we can combine this information. And the first thing I see is that triangle SAR and TBR share angle R. And they also both have right angles right here. And by double angle similarities, that means that these two angles are equal. So the ratio is BR, the ratio of these triangles is BR over AR, which is 6 over 12 plus 6, which is equal to 1/3. Okay, So let's call BT y. Since the ratio is 1 to 3, then SA is equal to 3y. And now we have so many lengths and so many equations that we can actually solve this problem. Here's how. We know from triangle BTR that x squared plus y squared using the Pythagorean theorem is equal to 36. Now from this triangle right here, that would be QSA. We know that using the Pythagorean theorem we have that x squared plus 9y squared equals 64. So we can do this equation minus the first equation, which would give us x squared minus x squared is 0. 9y squared minus y squared gives us 8y squared is equal to 64 minus 36, which is 28. So y squared equals 7 over 2. Okay. Now let's plug in y squared back into this first equation right here. So we have x squared plus 7 over 2 equals 36. Because remember, we're trying to find x. So x squared is equal to 36 minus 7 over 2. 36 is just 72 over 2 minus 7 over 2. That gives us 65 over 2. So the square root of x is equal to square root of 65 over square root of 2. So that's x. So QP, the side length that we're trying to find, is equal to the square root of 65 times the square root of 2, divided by the square root of 2 times 2. 2 divided by the square root of 2, that just gives the square root of 2. So we have square root of 65 times square root of 2. So in the original problem, though, it's asking us to find the square of the length of QP. Square root of 65 times square root of 2 is just square root of 130. And if we square that, let's head back there. If we are to square that, we get an answer of 130. So our final answer for this problem is 130, and we're done with the hardest problem of today's video. Thank you for attending today's session. Today's class was the last class of the AMC 10 bootcamp, and as always, you can find your homework and this week's handout at thepuzzle.com/courses/AMC-10-crash-course. Good luck on the AMC 10-12 exams, and we really hope that you'll be able to achieve your goals. Thank you, everyone, and bye.